Hello everyone, welcome back. I'm Alok Kumar and today it is going to be the final lecture on matrices and determinants. We've already covered a lot of material and today among other things we will see how matrix theory can be elegantly applied to investigate the system of linear equations as regards their solutions. So let me now quickly share my screen with you all and start the lecture. Okay, so there we go. So I will pick up from where I have left off last time. So let me do a problem on determinants. So we are given delta 1 is BC minus A square. It's a 3 by 3, CA minus B square, AB minus C square. And the second row reads CA minus B square, AB minus C square, BC minus A square. And the third row goes like AB minus C square, BC minus A square, CA minus B square. There is another determinant, delta 2, and the elements are first row A square, C square, 2AC minus B square, second row 2AB minus C square, B square, and A square, and the third row is B square, 2BC minus A square, and C square. We are asked to find delta 1 over delta 2, given that delta 2 is not 0, means assume that the numbers A, B, C are such that delta 2 is not 0. Otherwise, of course, it won't make any sense. So what comes to your mind first when we see a problem like this? If you ask me, I would say that at first go, they look quite unrelated. What delta 1 may have to do with delta 2? The elements have nothing in common. In fact, you have got CA minus B squared, and you have got here 2AC minus B squared. No such luck. So what I do, that I will try to look for some other determinant through which these two are related. That also is idea sometimes. So let's think of a determinant delta, and let me give it to you, ABC and BC and CAB. And do you see now what delta has to do with delta 1? What delta has to do with delta 1? Or for that matter, delta 2? So first we'll answer this question. What delta has to do with delta 1? If you look at elements of delta 1 closely, you will find that it has got BC minus A squared, which I can think of as the cofactor of element A, that is BC minus A squared. So if I write the cofactor of element of this one, means given a matrix Aij, that call it A, and you are writing a matrix B whose elements are cofactor of the elements of A. So this is n by n, this is also n by n. So we know that determinant of B has got some good relation with the determinant of A. So we are trying to exploit that. Now this is A. So this A has got BC minus A squared. That's the cofactor here. So let me denote it by something like, say that delta, I'll not name it. It will of course become delta 1 in the end. So let's forget it is delta 1. I'm just writing. Now BC minus A squared. Similarly, the second term will become CA minus B squared. This will become AB minus C squared. Again, you go further down. It is CA minus B squared, cofactor of B, of course with sign. So this is this B goes off, and this one. Then again AB minus C squared, and then BC minus A squared, and third row is also completed, A minus C squared, BC minus A squared, and CA minus B squared. So we see that delta 1 is indeed the determinant of cofactors of elements of delta. And so we know by a result, by a theorem, that delta 1 equals delta square. In fact, delta 1 is delta to the power n minus 1 if n is the order of, if n is the order of a square matrix n, a square matrix A. So we have already got this kind of thing. Delta 1 For our case, n equal to 3 because 3 by 3. So we get delta 1 is delta squared. Let's look at delta 2. Delta 2, we have term like a squared, c squared, 2ac minus b squared. So let me write the first element that I'll write here. So this is you have got a squared and c squared and 2ac minus b squared. That is your delta 2. This is the first row of delta 2. Let me look at it that can I get two matrices to determinant, suitable determinant, such that I have to create this first row and I have to create this column, this first column, second column, and third column, so that when I multiply, I am able to get a squared, c squared, and 2ac minus b squared. Let's rewrite a squared. If I write a squared as a times, so let me write in some other manner so that we can be clear what we're writing. So a into minus a plus b times minus c plus c times b. C squared I can write as a times b plus b times minus a and plus c times c. And 2ac minus b squared happens to be a times c plus b times negative of b and plus c times a. Notice how I have written this in bracket negative a, negative c, negative b. So these brackets, they will go into column. So they will go into column. And a, b, c, which are not in bracket, that is your row. So it means if this structure is followed, if I write a, b, c in the first determinant, in the first row, and then I write here in the second determinant, first column. So this is first row R1, and I'm filling column 1, column 2, column 3. So if column 1, it goes like negative of a. So if I write like this, or so this is this is plus a. So we write a, and then minus c, and then b, and then we write b, and then negative a, and then c. This should be c, and so this is c, and then we write c, and then negative b, and then a. So let me just quickly write this, that we are going like this. So we are writing a, b, and c. So this is a, b, and c, and then we wrote this one minus c, minus c, minus b, and b, c, a. Let me check this one. A squared is all right, c squared also is all right, and then 2ac minus b squared I can write as ac plus minus b plus ca. That's all right. So if I write like this abc, then I'll write abc, bca, and cab. Once that is done, then my job is easy. So then my job is easy, and what I will do, that I will say that our delta 2 is nothing but delta square, because if you look at this determinant, I can interchange ABC and BCA, and this goes in the third row, but then negative comes, and again I take negative out, and so ultimately you are back with ABC, BCA, and CAB. That's the original delta, and so delta 2 is delta squared. So we have found delta 2 is delta squared by some other logic, and delta 1 also delta squared by another piece of logic. So once we just simply multiplied in delta 2, in delta 1, we said the connection was through the cofactor of the determinant. And because both are equal, so our answer becomes the delta 1 over delta 2, that equals 1. So look how good the problem was, that it was two things and seemingly unrelated, delta 1, delta 2, but we found a common connection through them, through the determinant delta, and that was ABC, BCA, and CAB. Our success was in trying to find an appropriate relation between delta 1 and delta, and that between delta 2 and delta, and that was our method in the solution of the problem. So let me go to the next problem now. This comes from some trigo also, but of course in the language of the matrices. So we have got ABC are angles of a triangle. So given ABC angles of a triangle, and we have got this determinant to evaluate negative 1 plus cos B, and cos B plus cos C, and cos of B then you have got cos of C plus cos of A, -1 plus cos A, cos of A, and then -1 plus cos B, -1 plus cos A, and -1. And if you have to evaluate this, let us write the name as delta. And now, how do you attack this problem? Do you find some kind of thing which you repeat often? If you had got a good pair of eyes, you would notice that you have got somewhere these things. Like maybe we can check that if we say C1 and C1 minus C3. Why? Because cos B, this is cos B, cos A, -1. You have got cos B, cos A, -1, and then cos B, cos A, -1. So it means I can transform C1 to C minus C3 and C2 to C2 minus C3, and C3 stays the same, C3 stays put. So let's copy C3 simply, cos of B, cosine of A, and -1. And here, when I perform C1 to C minus C3, then I get here negative of 1, and then I get cos of C, and then I get cos of B. And similarly, in column 2, I get cos of C, negative of 1, cos of A. It looks more pleasing now because you have got everywhere on the diagonals -1, -1, -1, and cos A, cos B, cos C in L shape. It's same thing here also, cos A, cos B, cos C. And so we can quickly use Sarah's rule to evaluate the determinant. Sarah's rule is quite handy these times. So it gives you -1 from the diagonal, and then plus, this is cos A, cos C, and cos B, that is 2 times, and negative. And in negative, you are getting minus of cosine squared B, then cosine squared C, and cosine squared A. Ultimately, this rewrites as -1 plus cos squared A plus cosine square of B, cosine square of C, and plus 2 cosine A, cosine B, cosine C. That's a familiar expression. I will have much to talk about it in the next couple of lines. Now, imagine that this is given to you and you don't know how to relate. So what I can do, I can start with A plus B is pi minus C, because angle of a triangle, and cosine of A plus B is cosine of pi minus C, that is negative cos C. I can write cos A cos B plus sine of A plus sine of B is negative of cosine C. Because I want 2 cos A cos B cos C, I can transpose cosine of C to the other side. This reflect this one, and then negative of sine A, and this is negative. So in fact, this will become positive. So sine A of sine B, I can square it, and I can get cos A cos B plus cos C whole square. It's sine squared A and sine squared B, which I can write, because there is no place for sine here, I can change this to 1 minus cos squared A and 1 minus cos squared B, and further expand 1 minus cos squared A plus cos squared B, and plus cos squared A times cos squared B. And this side, so this side becomes now cos squared A plus cos squared B times cos squared B plus 2 cos A cos B cos C plus cos squared C equals 1 minus cos squared A minus cos squared B and plus cos squared A cos squared B. That happily cancels out, and we are good, and we get an identity, that is cos squared A plus cos squared B plus cos squared C plus 2 times cos A cos B cos C equals 1. This holds in a triangle. And look at now what we got. We got -1 plus this, and so this becomes 0. And so our answer for this problem becomes that this is 0. So let me have a second solution, and it is surprising in a way that it makes use of projection formula. Now, where does that come from? So let's again look at the determinant, that our determinant, after I simplified it, that was negative 1, negative 1, negative 1. So we have got negative 1, negative 1, negative 1. And then we have cos A, cos B, and cos of C. And similarly, you have cos of A, cos of B, and cos C. And this we want to evaluate. Let me remember that if I write A cos B plus B cos A, that gives me C. If I write A cos C plus C cos A, that gives me B. And if I write B cos C plus C cos B, that gives me A. These are called projection formulae, and I plan to use it here. So what I do, that I multiply the columns with, this is A, because cos C and cos B is there. So A, and this B, and this C. So it means I will write 1 over ABC, and you have got negative A cos C, A cos B. This is B cos C, negative B, and B cos A, and C cos B, C cos A, and negative C. Next step would be that whatever I did, I will now use the rows. So I will use R1, I will use rather columns. So let me erase that. In column, I will get C1 is C1 plus C2 plus C3. That means that in the first column, I'll get negative A plus B cos C plus C cos B. I'll get A cos C, negative B plus C cos A, and I will get A cos B plus B cos A, negative C, and these all are as it is copied. And so we know that because the first column elements, they become all 0, 0, 0 by the virtue of this projection formulae. Look at it, B cos C plus C cos B and other thing. And so it so happens that this all are 0. And so we again get the answer that our determinant delta happens to be 0. So that's what we do in this one. Now let me begin the discussion of, or let me change the color maybe, and let me begin the discussion of application of matrix theory. So application of matrices to linear equations. That's one of the topics that gets to see a lot of problems in both JEE Mains and Advanced. And so you do well to keep an eye out for them. Now, what I will do, that I will do these problems using the concept of rank. But for rank, I have to define some things first. So first I define the background material. That is, first is 3 elementary. So I write so that you understand properly. So 3 elementary row operations. So first I define 3 elementary row operations. That's first operation is, I will just write Rij, meaning that interchange. This means interchange the ith row, interchange the ith row with the jth row. That is your notation Rij. The second operation will be called Cri, meaning that multiplying the ith row by a scalar C, which is not 0, otherwise it just vanishes. So there is no point. So scalar C not 0. And third, I will denote it by Rij and C, and I will read as that adding to the ith row, C times the jth row. Means you are adding to the ith row, so you are changing ith row Ci or Ri, ith row Ri, and you are changing Ri to Ri, and plus you are adding to ith row C times a scalar times the jth row. So that is called this one. So Rij. These 3 are described as elementary row operations. They are very important, elementary row operations. And as we will see, that elementary row operations means that we already have this kind of thing, that we just have this kind of thing, elementary row operations, let me just take a moment to find and share some document. Okay, so let me save again because there's some problems going on. Okay, just bear with me. Okay, we are good. Okay, so now what happens that we are define these three row operations, Rij, Cri, and Rijc. And now what I can do is that I can define using this one some new thing, and that is called row reduced. It is called row reduced echelon form. And essentially this means that given a matrix, so given a matrix and we have to follow some steps. So first step is that the first non-zero element, the first non-zero element in every non-zero row, is one. It's called the leading one. It's called the leading one. So let me write along with this one matrix. So suppose you have got 1, 3, and 8, and so you have got 0, 1, and 5, and 0, 0, and 2. So this one is called the leading one in the first row. This one is called the leading one in the second row, and so on. So the first non-zero element in every non-zero row is 1, called the leading one. Here it is 2. So it does not follow this pattern. And second, you are saying, and let me tell you non-zero row. Non-zero row means that a zero row means that every element in that row is 0. So it means that a non-zero row will be a row in which at least one element is non-zero. So we are negating the 0 row. Second thing will be that what you are saying is that each column that contains the leading one. So each column that contains the leading one. So leading one, this one and this one, has all its elements below it as 0. Means, see, look at the first column. This is first. This is 1, and everywhere it is 0 after below 1. And similarly here, first is this one 1, in second row leading is this one. So second column below 1 we have got 0. This pattern will be followed. And third, we will say that the non-zero rows will occur. So they occur above the zero rows if any. Like you see that suppose we have got 1, 3, 5, 0, 1, 2, and 0, 0, 0. That's all right because that's a 0 row. So non-zero rows are these two. So non-zero rows occur above the 0 row if any. And last is that the leading one of any row. So the leading one of any row, say this row, this one, second row, leading of any row, and it will lie. So this must lie to the right of the column in which the leading one of the previous row happens. So let me read it again. It says that the leading one of every row, any row, must lie to the right of the column in which the leading one of the previous row happens. Means that you have got this one and this one, so they are all shifted towards right. So we can have this. So this is called this one. And based on this, now is the time to define rank of a matrix. So this rank of a matrix is called that it is the number of non-zero rows in its reduced form, in its reduced echelon form. So it means that number of non-zero rows in a matrix. So in a matrix, in its reduced echelon form, and we are always doing row reduction. So row reduced, we'll say row, although we can do on columns also, but we prefer row. Now, if that is there, then we find row rank, and we denote it by row of A, that is rank of A. So it's number of non-zero rows in its reduced echelon form. Now, let me give you the criteria for the solutions. So we have technically Ax equal to 0, one system. This system is called homogeneous. And one, you have got Ax equal to B. This system is called non-homogeneous. Now, Ax equal to 0, to give you an idea, suppose equation is 3x plus 4y plus 5g is 0, and 4x minus y plus g equal to 0, and x plus y plus 11g is 0, then I would say that I can express this in matrix notation as 3, 4, 5, 4, negative 1, 1, and 1, 1, 11. And then here x, y, and g, and right side is 0, 0, 0. So that's your Ax equal to 0. So we have got homogeneous and non-homogeneous. So now if homogeneous is there, then we have got that det of A is not 0 and det of A is 0. So det of A is not 0 means you have got unique solution. And this is just the trivial solution, that is x equal to 0. And if det A is 0, then you get infinite solution. This system is always consistent. So no case of no solution. Means it always must have at least one solution. In fact, either infinite or unique. And unique solution is just x equal to 0. Det A is not 0. In fact, det of not 0 is same as, you will find that in this case rank of A will be 3 if A is 3 by 3, and in this case rank of A is less than 3. So this is for homogeneous. For non-homogeneous, situation is a little complicated. So Ax is B. What we do, that we first form the matrix AB, we combine this in AB, and so we find rank A, and we also find rank of A combined with B. These two we find rank of this one. The moment we find this rank, then we say like this, that if rank of A is not rank of A combined with B, this one, then we say inconsistent. So inconsistent means no solution. That's no solution. Or if you have got rank of A is rank of AB, rank is same, say R, then we have got two cases. Look at the flowchart, that if R is less than N, or R can be equal to N. If R less than N, N is the A N by N matrix. If R is less than N, then you get infinite solution. And if R is N, then you get unique solution. So here you get three things: no solution, unique solution, and infinite solution. Compare with homogeneous case, there is nothing like no solution. No solution. You have got infinite either or unique solution. And all this we do with theory of matrices because it's very powerful. And let me see how we can apply it to some problem. So my first example would take this one, that we have to solve a system. This is x plus 2y plus 3g equals 0, and 3x plus 4y plus 4g equal to 0, and 7x plus 10y plus 12g equal to 0. So we have to investigate whether the system has unique solution or infinite solution or no solution. So let's write this as Ax equal to 0 with A as 1, 2, and 3, 3, 4, 4, and 7, 10, and 12. And your X happens to be the column matrix X, Y, and G. So as you know, this is 3 by 3, this is 3 by 1. So we are good. Ax is, so it is conformable. A is 3 by 3, X is 3 by 1, and so result is 3 by 1. That's all right. Now let's find the rank of A. So I'll reduce A to the row echelon form. So in row echelon form that I talked about, that row echelon form. So in row echelon form, I'll first leave the row unchanged, first row, that's 1, 2, 3. And then R2, I'll write R2 is R2 minus R2 minus 3R1. 3R1 because of course we want first these and these to become 0. So we can write here 1, 2, 3, and this is 0, and then 3. So that is -2 and -5. And similarly, I write R3 change to R3 minus 7R1, and that gives me 0 and 7R1, so -4 and -9. So we already have got this leading 1 and then zeros. Now my goal is to make this 0 -4. So for that, I leave 1, 2, 3 unchanged, 0, -2, -5 unchanged, and I change R3 to R3 becomes R3 changed to R3 minus 2R2. That's to produce 0, so 0, 0, and this is 1. So we have got finally this form. So there is no non-zero row. There is no zero row. All rows are non-zero. And so rank of A is 3 because number of non-zero row, this is a non-zero row. Non-zero row means that at least one element is 0. So it doesn't have 0 row. So rank of A is 3. And if rank of A is 3, it means same thing that data of A is not 0. And so you will get unique solution that is 0, 0, 0. And let us check this. This looks like x plus 2y plus 3z is 0, reduced form, minus 2y minus 5j is 0, and g is 0. And so you are seeing that we can work our way upwards. So g is 0, and then y is 0, and consequently x is 0. So here we have got the case the data of A is not 0, ax equal to 0. So of course solution is unique. That's the trivial solution. 0, 0, 0 is the only solution. This is number 1. Coming to next, that let me do one other thing that will tell you that how we are creating the other things. For example, say we have got find lambda and mu that belongs to R, maybe lambda and mu, such that you have got x plus y plus g equal to 6, x plus 2y plus 3z equal to 10, and x plus 2y plus lambda g equals mu. So you want lambda mu element of R such that system has no solution, unique solution, and third, infinite solution. So you want those lambda u, characterize those lambda mu real numbers such that this system has either no solution or unique solution or infinite solution. Let's again use the language of matrix in the solution. So we'll take our A as the coefficient matrix 1, 1, 1, 1, 2, 3, and 1, 2 lambda. My x is as usual x, y, and g, and my B column vector is 6, 10, and mu, and my equation reads as Ax equal to B. Let me find the rank. So I will combine AB, this matrix, and this AB, I'll find this writing 1, 1, 1, 1, 2, 3, 1, 2 lambda. And what we can do is that we can put a bar here to remind us that this is on the other side, 16 and mu. They are on the right side, 16 and mu. And let's do the same thing and try to row reduce them, row reduce to echelon form using elementary row transformation. Elementary, that 3 transformations we said, elementary row operations. Let's use those operations. So you will get here 1, 1, 1, 6. And then I want to change, so I'll write R2, R2 minus R1 to make this and this leading these zeros. And then R3 also, I can write R3 minus R1. So R1 stays the same, and R2 transforms, subtract R1 from R2, that is 0. This is 1, and this is 2, and this is 4. And similarly, the next step would be 0, and then 1, and then lambda minus 1, and then mu minus 6. That is your next step, lambda minus 1. So let me erase and write it clearly that this is lambda minus 1. That's lambda minus 1. Your next step would be that now you want a 0 over here. So again, keep the first two rows as they are, 1, 1, 6, 0, 1, 2, 4, and write R3 change to R3 minus R2. That is 0, 0, lambda minus 3, and mu minus 10. Now is the time to analyze things properly. So what I'll do that I will think of this lambda minus 3. So if lambda minus 3 is not 0, that's my first case, not 0 means my A is equivalent to now A matrix is 1, 1, 1, coefficient matrix 0, 1, 2, and 0, 0, lambda minus is not 0 means here something not 0, say 5 or whatever you like, not 0. So it means rank of A is the number of non-zero rows in this form, and number of non-zero rows is clearly 3, and so it is 3. Rank of A is 3. Now this is not 0, so lambda minus 3 is not 0. Now let's take off rank of AB. So rank of AB, for that I will write this matrix AB, and that is equivalent to, that is 1, 1, 1, 6, 0, 1, 2, 4. I forget the bar here. 0, 0, lambda minus 3. So this is not 0, let's write, and mu minus 10. Because this element is not 0, mu is whether 10 or not 10, does not matter. One element is not 0. So this row is not a 0 row. That is, it's a non-zero row. It's a non-zero row. At least one element is non-zero. And so, in fact, rank of AB also is 3. Because rank of AB is 3, so it means if lambda is not 3, then you are getting what is called unique solution. So if lambda, so I will record this finding as lambda is not 3, and mu there is no condition. So let's say that mu is element of R. So lambda is not 3, and mu belongs to R. This case is our unique solution because both matrices have same rank and rank is 3. So let's discuss lambda is 3 now. If lambda is 3, then obviously A matrix becomes 1, 1, 1, 0, 1, 2, and 0, 0, 0. So now rank of A is reduced, it becomes 2. Rank of A is 2. And when I talk of AB, this AB combined matrix, then it is 1, 1, 1, 6, 0, 1, 2, 4, 0, 0, 0, and this is mu minus 10. So if mu minus 10 is 0, then rank of AB is again 2. But if mu minus 10 is not 0, then rank of AB is 3. So if lambda is 3 and mu suppose is 10, if mu is 10, then you are getting rank of A is 2 and rank of A and B combined is 2. If that is both rank are same, but 2 is less than 3, rank is less than the number of this one, the order of matrix. And so in this case, you will find that lambda is 3, mu is 10 will give rise to infinite solution. Infinite solution. And if lambda is 3 and mu is not 10, then we see that in this case, rank of A, that was 2 because lambda is 3, and rank of AB combined, that rank is 3. So these don't match. And so system is inconsistent because it's not same, inconsistent. And so in this, it means you get here no solution. So we said in conclusion that if lambda is 3 and mu is not 10, then inconsistent, no solution. If lambda is 3, mu equal to 10, infinite solution. And if lambda is not 3, then unique solution. So you find that lambda is not 3 and mu can be anything, does not matter, whatever it is. And so we get this kind of answer that, okay, this is also correct. Let me now do one other type of problem and where you have got some more challenge. So now we have got a matrix in that is your same thing, x plus y plus g equal to 1, x plus 2y, x plus 2y and plus 4g equal to k, and x plus 4y plus 10g equal to k squared. So if that is the case, k squared, then what I can do is, same question remains same, that here also you want to find all k belong to R such that system has no solution, then second infinite solution, and third is unique solution. So you want to investigate again those numbers, that for what values of k it is possible. So let me again write ax equal to b, where a equals 1 1 1 1 2 4 1 4 10, and your b is 1k k square, and x as usual is x y and g, the column matrix x y and g. Now let me find the rank. So a b, it will be given by 1 1 1, and then 1 2 4 and 1 4 10, and then 1 k and k square. I'll have to remind myself that this bar is there, so you have on the right side of this. Let us row reduce this. So let's make these two 0 by elementary row operations. So 1 1 1 1, first row remains unchanged. R2 transforms to R2 minus R1, that's 1 minus 1 0, that is 1, that's 3, that's k minus 1. And R3 transforms to R3 minus R1 again, so that number is 0, and then 3, and then 9, and then k squared minus 1. Now my aim is to make this element 0, and so this is again same thing, that we will write first two same. So this is 1 1 1 and 1, and 0 1 3 and k minus 1, and I can write R3, I can change to R3 minus 3 R2, so that becomes 0, and that gives you 0 and 0, and here you are getting now k squared minus 3k and plus 2. So we get already that a is equivalent to 1 1 1 0 1 3 0 0 0. So rank of a is just 2. It's not 3 now, and it is 2 fixed because there is no variable here. And rank of AB depends on, so AB is, you forget the bar now because you're considering the whole 1 0 1 3 k minus 1 0 0 0, and this is k minus 1 k minus 2. So now rank of AB is 2 if k minus 1 k minus 2 equals 0, and equal to 3 if k minus 1 k minus 2 is not equal to 0. Means here k is 1 or 2, and here k is neither 1 nor 2. Now as we see that rank of A, so if rank of A, when rank of A is 2 and rank of AB is 3, this is inconsistent, and so we find that in this case there is no solution, and this case is captured by 3, means k is not 1 and 2. So if k is not 1 and 2, then we have got no solution. And when k is 1 or 2, so when k is 1 or 2, then we are seeing that rank of A is 2, and rank of A combined with B also is 2. And so in this case, we have got infinite solution, not unique, because this 2 is less than 3, which is the matrix was A 3 by 3. So it means we have said that either it has got no solution or infinite solution. There is no k for which this has got unique solution. Means if the question is unique solution, you will say that k is empty set. So k element of phi means there is nothing, no value of k. So either you have got no solution or you have got infinite. You have got no solution for k equal to not 1 and 2, and everywhere k equal to 1 2 you have got infinite solution. Let us again do a couple of more to understand how this all happening. And so the other example that I'll take is this one, that we want now to find out lambda belong to R such that the system has solutions. We have not said unique or infinite, so we can discuss them. So that system is lambda x plus 2y minus 2g minus 1 equal to 0, 4x plus 2 lambda y minus g minus 2 is 0, and you have got 6x plus 6y plus lambda g minus 3 equal to 0. Again, I can put this one, that A, matrix A. So the matrix A I will write as usual is lambda 2 minus 2. This is 4, 2 lambda negative 1, and 6, 6 lambda. And your X is as usual X, Y, and G. And you have got B as 1, 2, and 3. So my system in matrix notation becomes AX equals B. Now let me find A. So this time, instead of this one, I will find det of A. So det of A means I have to find lambda 2 minus 2, 4, 2 lambda negative 1, and 6, 6, and lambda. Now I see that if I write here C2, so I can write first of all that C3 change to C3 and then plus C2. So if I change that C3 plus C2, if I change, so I will get here lambda 4 and 6. This is 2, 2 lambda 6. This is 0, minus 1 plus 2 lambda. And this is lambda plus 6. And once I've got a 0, I can take out now some common. And I can also write C1 I can change. I can write C1 as C1 minus C2 because 6 will become 0. So C1 is this one. So I can write lambda minus 2 and 4 minus 2 lambda. So 2 times 2 minus lambda, this is 0. And this is 2, 2 lambda 6 and 0 minus 1 plus 2 lambda, lambda plus 6. And this equals, you have got a common. So I can take common 2 times lambda minus 2 from the first column. So that becomes 1, negative 2, and 0. And this becomes 1 lambda and 3. And then you have got 0 and minus 1 plus 2 lambda and lambda plus 6. Now I can expand them. So we can use the Saras rule because it's quite effective again here. So you have got 2 lambda minus 2. And then Saras rule I first form in this. I recall that I first form this one, then these two and this, and then finally this one and these two. This is what we do. So this is lambda times lambda plus 6, and then negative of, then signs are negative, minus 2 lambda plus 6, and plus 3 times minus 1 plus 2 lambda. That gives me 2 times lambda minus 2 and lambda square plus 6 lambda and minus, and this gives me minus 2 lambda minus 12, negative 3, and then plus 6 lambda. And then we have got this as 2 times lambda minus 2. You have got lambda squared and plus 2 lambda. So lambda squared plus 2 lambda and plus 15. Now for this polynomial, for this lambda, for this quadratic discriminant is negative, and so no real solution. So if I write det of A is 0, this implies lambda equal to 2, lambda element of R. So we have got only one value, lambda equal to 2. So let's discuss for lambda equal to 2. So if lambda equal to 2, then we can discuss this, that okay, we have got the equation as 2, 2, negative 2, and then 1. Let's check 2, 2, negative 2. So that is here, that lambda, we are getting lambda. So we are getting 2, 2, negative 2 here, then 4, and then 4, and then minus 1, and 6, 6, and 2. So that's 4, 4, and negative 1. Here already it is 2, and 6, 6, 2, and 3. We want to discuss this system. Now this system will have that it is equivalent to, let's write 2, 2, negative 2, 1, leave unchanged, and let's apply R2 to R2 minus 2R1. that gives me here 0, and here 0 and 3, and this is 0. And also apply, let me apply R3 to R3 minus 3R1. That gives me 0, 0, and 8, and also 0. I can go on, but then it will be stopped here. So I will write here this system as 2x plus 2y minus 2g equal to 1. So that's all right, that we are getting separately. And then we are also getting here 3z equal to 0, and we are getting 8g equal to 0. So if that is the case, then we can have this kind of thing, that we have got from here g equal to 0 and x plus y equal to 1 over 2. It tells you that in this case, lambda equal to, you have got infinite solution. I can capture solutions by write x equal to t, and so y is 1 over 2 minus t, and so x, y, g solution will be given by that t and then half minus t and then 0. And it tells you that for lambda equal to 2, the system has infinite solutions. We have described all solutions using this technique. Let us look again at a problem. So we have got that you want the value of lambda. So you want to find the lambda element of R such that the system x plus y minus 3g equal to 0, and then 1 plus lambda x plus 2 plus lambda y minus 8g equal to 0, and x minus 1 plus lambda y plus 2 plus lambda g equal to 0 has infinite solution. You want those lambda such that it is infinite solutions. So again, we write as A. So this matrix A is nothing but 1, 1, negative 3, 1 plus lambda, 2 plus lambda, negative 8, and then 1 minus 1 plus lambda and 2 plus lambda. And you have got this Ax equal to 0, homogeneous case, the easiest one. So x is x, y, and g. So you know that if you want this system to have infinite solution, then it is both necessary and sufficient. So it is both necessary and sufficient that this det of A is 0. So det of A is 0 is necessary and sufficient for infinite solution, infinite solution. So we'll find det of A and then we'll solve the resulting equation. So det of A equals 1, 1, negative 3, 1 plus lambda, 2 plus lambda, negative 8, and 1 and minus 1 minus lambda, 2 plus lambda. So I can use that this, I can reduce this by using change C2 to C2 minus C1. So that is 1, 1 plus lambda and 1 step out, and you are getting this is 0, and then 2 plus this is 1, and minus 2 minus lambda. And then we can also write change C3 to C3 plus 3C1. So we create here and here 2 0. This is 0 and 3. So I will get minus 5 plus 3 lambda. And this is 3. This is 5 plus lambda. And now I can quickly evaluate them. And this answer is that det of A will be 5 plus lambda. And this is expanding about this one. And minus of minus 2 minus lambda minus 5 plus 3 lambda. That gives me 5 plus lambda. And that gives me negative of negative 2 minus lambda and 3 lambda minus 5. And that is 5 plus lambda plus lambda plus 2 and 3 lambda minus 5 is 0. So that equals 5 plus lambda plus this is 3 lambda squared and 3 lambda squared plus lambda minus 10. So I get 3 lambda squared plus 2 lambda minus 5. So let's calculate what is det of A is 0. Det of A is 0 implies that 3 lambda squared plus 2 lambda minus 5 equals 0. That equals 0. And so we see 1 is a root. We can see exactly. So 3 lambda is squared, and then minus 3 lambda plus 5 lambda minus 5 equals 0. I can factorize 3 lambda, lambda minus 1 plus 5 times lambda minus 1 is 0. So lambda minus 1 times 3 lambda plus 5 equals 0. So in this case, we are getting lambda equal to 1, and lambda is negative of 5 over 3. So it means we are getting that these two are the things for which we have got infinite solutions. And let us show you that how lambda equal to 1 you will have a solution. So for lambda equal to 1, your A becomes, let us look up. So for lambda equal to 1, then when we look up, we are finding this kind of thing, 1, 1, minus 3, and this one. So for lambda equal to 1, let me copy it first, that A was 1, 1, negative 3, 1 plus lambda, 2 plus lambda, negative 8, and 1 minus 1 minus lambda, and 2 plus lambda. And so for lambda equal to 1, this A becomes 1, 1, negative 3, then this is 2, and then lambda is 1. So this is 3 and minus 8 and 1, and lambda is 1. That becomes minus of 2, and this is lambda is 1. This becomes 3. So let me row reduce it. So this is 1, 1, negative 3. So first I want to make these two zeros. So I'll apply R2 goes to R2 minus 2R1. So 1, 1, negative 3. This is 0, and this is 3 minus 2, that's 1, and this is minus 6, and then minus 8, so that becomes negative of 2. And I also apply R3. So R3 goes to R3 minus R1. So that's the subtract 0, and then minus 3, and then this is 6. And so next step would be to make here 0. So I'll now write this as 1, 1, negative 3, 0, 1, negative 2. And then I can use that this R3, I can write as R3 and plus 3R2. That means that you have got 0, 0, and R3 plus 3R2. So of course this will become 0. You can see also that third row is a multiple now of second row. And if you multiply with negative 3, you will get the third row. So you already know that in this stage, R3 was nothing but negative 3R2. And so it's a multiple. And so you're getting a 0 matrix here, 0, 0, 0, a 0 row here, this one. And so you cannot do further. So rank of A is 2. That tells you that you have got infinite solution that we found earlier also. And we can also capture solution. So we can, now system becomes 1, 1, negative 3, 0, 1, negative 2, 0, 0, 0, and x, y, g, and that equals homogeneous 0, 0, 0. If that is the case, we will have now x plus y minus 3g is 0, and we have y minus 2g is 0, and 0 is 0 gives nothing. Again, work our way like this. So y equal to 2z, so I can write g equal to t, then y will be 2t, and from the first equation, x plus y minus 3z is 0, that gives you x plus y is 2t, and minus 3t is 0, and so you get x minus t is 0, so x equals t. And so your solution, order triple, that becomes t, and then 2t, and then t, that is your x, y, and z, and that is your t times 1 to 1 t element of R. Of course, 0, 0, 0 is always solution. So you see here that again you have got here infinite solution. So we have found that in this case also we have got infinite solutions. Similarly, we can do things for lambda equal to negative 5 or 3. They will have different kind of solutions. So that's all for today. Let me stop sharing and come back. So that's all for today. Let us connect tomorrow.